So let's talk about the next level of understanding of protein structure, which, like I said before, the amino acids themselves are not so interesting from a functional point of view by themselves. But when you put them together, that's where things really start to get interesting. Of course, that involves linking amino acids together into this interaction known as the peptide bond, right? So what happens when you put condensed two amino acids into a peptide bond? Okay, so that condensation reaction essentially involves the nucleophilic substitution of the alpha amino group, right, from one amino acid, excuse me, for the oxygen, the non-carbonyl oxygen of the carboxylate group of another, right? And that dehydration condensation reaction then with release of water, right? Because we're going to give up a proton. We're going to give up a proton here, right? And then that hydroxyl, and we'll pull another proton off as well. If this was protonated, for example, we leave two hydrogens here and an oxygen here, release of water to give that covalently bonded pair of amino acids through an amide bond. Okay, now there's one important thing to note here, which is that the amide bond formation results in a polarized polymer, right? So proteins, of course, have either an amino terminus or a carboxy terminus, and that is a consequence of the fact that each amino acid has an alpha amino group and a carboxy terminal, alpha carboxyl group. You condense two of those to form an amide bond, you end up with a linked polymer that has an amino side and a carboxyl side. And of course, you keep adding amino acids, right, on this side, that will just continue, right? So you guys all remember that proteins linked through amide bonds have one end has an amino group hanging off, the other end has a carboxyl group hanging off. Okay. Now, the peptide bond has a lot of really interesting properties. And of course, if we just stop with two amino acids, that's not so interesting, right? In addition, one of those properties that's worth thinking about is any given amide bond, right? Even just this pair, this bond formation is not favorable, right? It's thermodynamically quite unfavorable to make that condensation reaction happen, which means that peptide bonds, amide bonds, are unstable, fundamentally unstable. 10 kilojoules per mole to get that amide bond to form and give us this linked pair of amino acids. Okay, that has interesting implications later, and we'll talk about those. Okay, so like I said, sticking just two amino acids together is kind of boring. So we put more and more of them together, stick a few of them together. You get, of course, a few amino acids together, like in this case, a tetrapeptide, glu-gly-allylase, EGAK. You get a oligopeptide, right? And at some point, you keep adding them together, right? So here's an example of that oligopeptide. There's the amino terminal amino acid. We got three amide bonds, right, between those central amino acids. There's the carboxyl terminal amino acid. You can keep doing this, keep stacking them up. You stack up a few up to a point. It's referred to as a polypeptide. And at some point, when there are enough of them there, you transition from a polypeptide to a protein. What that exact transition point is when you stop, technically any protein is a polypeptide. Most people don't refer to like decently large proteins as polypeptides, even though they are. So the nomenclature there is a little fuzzy, but you string them together and of course you then get a protein. Okay, that sequence of amino acids, in this case glu-gly-allylase, that sequence of amino acids is fundamentally the core part of the primary structure of a protein. It's linear sequence of amino acids. But there's a little more to it than that. There are additional modifications to a protein sequence you would consider part of its primary sequence. And of course, the primary sequence, when people write it down, gets this sort of 1 degree sign, right? Okay. So for example, here's bovine insulin. Bovine insulin is synthesized as a single linear chain. It sort of folds up, and a set of its cysteines form, as we just talked about, disulfide bonds here, right? Okay. The chain is then cut, and the 2 chains are held together by those internal disulfide bonds. That bonding structure, those cross-linked disulfide cross-links, are all part of bovine insulin's primary sequence. And there are additional modifications that would technically be considered part of a protein's primary sequence. For example, stable phosphorylations, right? Hydroxylation of prolines, there's an example, right? Or hydroxylations of lysines, right? And there are other post-translational modifications like that that are considered to be part of a protein's primary sequence. Okay, so there's another fundamental part or property of the amide bond that is extremely important for thinking about protein structure. And that's the fact that if you think about your organic chemistry, right, you'll remember that the electrons in that carbonyl oxygen don't just sort of sit there, right? It's not just a stable carbonyl. They're in resonance, right, with the electrons, that unpaired pair of valence electrons in the nitrogen. And these guys can go back and forth, right? Which in sort of simple sort of electron pushing notation would look like a pair of resonance structures. In terms of the actual orbital structure, what that means is that the carbon atom, the oxygen atom, and the nitrogen atom all share a molecular pi bonding orbital, right? Which, if you remember your organic chemistry, has these electron clouds distributed above and below the plane, the bonding plane of those 3 atoms. What that means, the nature of these pi bonding orbitals, is that the rotational degrees of freedom around the carbon-nitrogen bond are not totally available. In other words, what this means is that the amide bond acts like a planar bonding interaction. So there's essentially a plane that can be defined between the amino proton and the oxygen, right? And with the carbon and the nitrogen in the amide bond in the center of that plane. And this bond basically acts like a planar group, right? So you don't have free rotation about the carbon-nitrogen bond of the amide bond. It more or less acts as sort of like a rigid body, sort of planar group. Now, having said that, even though it's not freely rotating, amide bonds do have 2 positions. Again, you may recall from your basic organic chemistry that you can arrange the amide bond with the hydrogen and the carbonyl oxygen on the same side of the bond, or you can arrange them on opposite sides of the carbon-nitrogen bond here, right? This configuration with them on the same side is, of course, known as the cis configuration, and the opposite side is, of course, the trans configuration. So that even though they're not freely rotating, right, the amide bond is stable, in principle, in one of 2 positions, either the cis configuration or the trans configuration. But it turns out for all but one amino acid, that cis-trans configuration is dramatically, like 1,000 to 1, pushed in the direction of the trans configuration, right? So that equilibrium, if we define the equilibrium between the cis and trans configuration, assume that it can jump back and forth in principle between one of the other configurations. For all of the amino acids, with one exception, that equilibrium constant is pushed to the 99.99% level into the trans configuration, right? The one exception to that is proline. If proline contributes the nitrogen here to the amide bond, that equilibrium constant drops by almost over 200-fold, 250-fold roughly, to basically about a factor of 4, right? So cysteine is the one amino acid that can actually readily or frequently, not infrequently, sometimes quite frequently, populate a cis amide bond configuration in an actual protein. Okay, so with that, next time we'll take up the next stages of protein structure on our way to understanding how the three-dimensional structures of proteins ultimately are put together.